Hey everyone, welcome back to the deep dive. You know the drill, right? We go deep, we get specific, we cut through all the noise, and by the end of it, you've got the knowledge, without feeling overwhelmed. And today, we're diving headfirst into something that's kinda unavoidable in the world of tech and code.
We're talking about errors, those little, or sometimes not so little, glitches that pop up when we're building algorithms and programs. And more importantly, we're going to figure out how to actually make sense of them, not just freak out when we see them.
Yeah, exactly. Nobody wants their program crashing, right? So for this deep dive, we've been poring over these fascinating YouTube transcripts.
From the Code Curious channel, hosted by Dan Burrow, who also happens to be a teacher at Riverside Brookfield High School.
So think of this as like a backstage pass to the world of coding, where we demystify those errors. Our mission today is to give you the tools, the insights, to not just understand these errors, but to really tackle them head on. So let's get started. Our source material lays out these 4 fundamental types of errors that programmers, anyone working with code, will bump into sooner or later.
And the first one on the list is the logic error.
Okay, logic error. So for those of us who aren't coding whizzes, break it down. What exactly are we talking about here?
A logic error, it's basically a flaw in the thinking behind your algorithm. And remember, an algorithm is just like a set of instructions, a step-by-step guide to solve a problem.
Right, like a recipe for the computer.
Exactly. So with a logic error, your program, it might actually run, it won't crash or anything, but it won't give you the result you expected. It's like you're following directions, but they lead you to the wrong place. You get somewhere, but it's not where you want it to be.
Okay, I'm starting to see the picture. And our source material gives this really clear example. An algorithm for assigning letter grades based on numerical scores. Like you get a 90, you get an A above 80, a B, and so on. Where could the logic go wrong there? I mean, it seems pretty straightforward.
Well, here's the catch. Let's say you get a score of 90, right? The program might see that 90 is greater than 89, so it's like, okay, that's an A, which is correct. But then it might just keep going, keep checking. It also sees that 90 is greater than 79, 69, and 59.
So it gives you all the grades.
Yep. You end up with A, B, C, and D all at once. Basically, the way it's written, it's not stopping after finding one match.
Oh, so it's not like those choose only one questions on a test.
Right. And Dan Burrow, the teacher in the videos, he points out that this kind of error, where you don't set those clear boundaries in the code, it's super common for beginners. It's that hurdle of going from like the logic in your head to the very precise language of code. But here's the thing. Sometimes this faulty logic, it might actually seem to work.
Wait, really? How's that possible?
Think about it. If you put in a 60, well, in our messed up example, 60 is only greater than 59, so it would give you a D, which is right. Same with like a 52, it wouldn't hit any of those grade cutoffs, so it'd probably fall into an F, also seemingly correct.
So you might think everything's fine, but it's not.
Exactly. It's like a trap. Those little moments where it seems to work, they can make you think your code is good to go, but it's not. That's why testing your code with a bunch of different inputs, it's absolutely crucial.
All right, that makes total sense.
Yeah.
So logic errors, they're like a flaw in the plan.
Yeah.
Then we have these things called syntax errors, right? That sounds more like a grammatical issue in the code itself.
Spot on. Syntax errors are all about breaking the rules of the programming language. Like, it's grammar rules. It's like, if you're writing an essay and you forget a period at the end of a sentence or you misspell a word, the computer, it can't even understand what you're trying to tell it if the syntax is wrong.
And in our source material, they list all these usual suspects. Missing colons, semicolons, parentheses, curly braces, all those little symbols that seem to make the coding world go round. Then there's like forgetting quotes around text or even messing up the indentation, which matters in some languages.
Yeah, it's like the computer saying, hold up, I don't even know what you're trying to say here.
Yeah. And in one of the Code Curious videos, Dan actually shows this little code snippet with like 4 syntax errors on purpose. A missing parenthesis, a curly brace gone astray, missing quotation marks. The works.
And these are the kinds of tiny mistakes, easy to miss, but they absolutely have to be fixed. It's like, you could have the most brilliant idea for a program, but if you've got a misplaced semicolon, the computer's not even going to try to run it.
It's like a typo bringing down the whole operation. Okay, next up we've got runtime errors. Now these sound a bit more dramatic? Like something goes wrong while the whole program is running?
It can be pretty dramatic, yeah. A runtime error, it happens while your program's in action. It might start up just fine, no problem, but then while it's chugging along, something happens that it just can't handle, and boom, it crashes.
So like a sudden system meltdown.
Pretty much. And this is what people often call a bug, like a little gremlin in the machine causing trouble.
Okay, so the program's running smoothly, then bam, it hits a wall. What kind of things trigger these mid-program crashes?
One classic example is trying to divide a number by 0. In math, that's just undefined, and when a program tries to do it, well, it usually freaks out and throws a runtime error. Another super common one is when the program's expecting a certain type of data, like a number, but it gets text instead.
Ah, like in that letter grade example.
Yeah.
What if it was in the letter A instead of, a number grade?
Exactly. The program's gonna be like, I don't know how to compare a letter to a number. This data type mismatch, in many languages, it'll cause a runtime error. That's why some languages make you specify the data type for each variable, like, is it a number, is it text, so it can catch these problems before they cause a crash.
So it's like a safety net for your code.
Yeah, basically. And then lastly, we have overflow errors. Now, these sound like we're pushing the computer to its absolute limit.
Like overloading the system.
Exactly. An overflow error happens when a calculation produces a result that's just too big, too huge for the computer to handle, given the memory it's allocated for that type of number. It's like, imagine you have one of those old calculators and you try to multiply, say, 100 by 100. The answer is 10,000, but if the calculator only has a 4-digit display...
Can't show the whole number.
Right. Programming languages, they have similar limitations. They can only handle numbers up to a certain size. So if you do a calculation that goes beyond that limit, you get an overflow error.
Okay, so we've got our 4 horsemen of the coding apocalypse. Logic errors, syntax errors, runtime errors, and overflow errors. Now, the million-dollar question. How do we actually find these bugs and squash them?
Well, starting with those pesky syntax errors, the good news is most IDEs, those are like the software environments where you write code, they're pretty good at catching those. They often give you instant feedback, like as you're typing, flagging any syntax issues, and even pointing to the exact line where the problem is. It's like having a grammar checker built right in.
That's pretty handy. So it's like you're writing code and it's like, nope, you missed a semicolon right there.
Yeah, pretty much. But here's a little caveat. Dan mentions in the videos that sometimes the IDE might highlight the line next to the actual error.
Yeah.
Like if you forget to close a parenthesis on one line, the error might show up on the following line because the computer's still waiting for that closing parenthesis. But overall, IDEs are a great first line of defense because honestly, your program won't even run if it's full of syntax errors.
You got to get the grammar right before you can even tell the computer what to do. Now, logic errors, those seem trickier because the program runs, right? Doesn't just crash immediately.
Right.
How do we go about hunting those down?
That's where test cases come in. Since the program runs, you got to be proactive, really put it through its paces, you give it specific inputs, and you check very carefully if the output matches what you intended. It's like being a detective. You present different scenarios, see if the story holds up.
Oh, I like that analogy.
Yeah, a good set of test cases, it's like interrogating your code. You're basically asking it, okay, if I give you this, what are you going to do? Is that the right answer?
So going back to that messed up letter grade algorithm, how would we design test cases to expose that logic flaw?
You'd pick different scores strategically. If you give it a 95 and it spits out A, B, C, and D, you know something's wrong. Same with an 82 giving you B, C, and D. But remember, some inputs like that 61 giving a D, those can trick you into thinking everything's fine. That's why it's not just about randomly trying numbers. You got to think about what each range of scores should produce.
So you're not just throwing darts at a dartboard, you're aiming for specific spots. And there's this idea of border cases, which our source emphasizes as really important. What are those exactly?
Border cases, they're like the edge cases, the values right on the border between different grades. Like for that algorithm, a score right around 89, like 89.5, even 90 itself. And then just below, like 89.4, those are super important because if your condition is just greater than 89, well, 89.5 might sneak in and get an A even though it shouldn't. These edge cases, they often reveal those subtle errors where the program's logic is just a tiny bit off.
So you're really poking at those boundaries to see if it behaves exactly how you want it to. Now, our source also mentions a couple ways to actually fix that flawed algorithm. What are the strategies there?
One common approach is to use these things called nested else-if statements. It's like creating a hierarchy of conditions. If the first one's true, like the grade is above 89, it displays the A and then just skips all the other conditions. That way you only get one grade. Another way is to use and conditions, so you're specifically defining the range for each grade. Like if the grade is greater than 79 A and D, less than or equal to 89, then it's a B.
So you're being super specific with the computer. Now, another technique for finding errors, especially in more complex parts of the code, is hand tracing. This sounds like we're going old school, almost pretending to be the computer ourselves.
Yeah, it is a bit like that. Hand tracing is really useful for understanding how loops, those repetitive parts of the code, actually work step by step. You basically go through the code line by line, and you keep track of all the variables, like what their values are at each step.
So you're basically stepping into the computer's shoes.
Right. And our source uses this example of an algorithm that's supposed to find the smallest number in a list, like, let's say 2, Nagri, 3, 5, 1, 10, 8. And it's flawed. It doesn't always find the correct minimum.
And hand tracing helps us see why.
Yeah. You make a little table and you track the variables, like what the current minimum is, what number the program's looking at, and so on. In that faulty example, the algorithm, it kind of messes up because it's only comparing each number to the one right after it.
So it might see that -3 is smaller than 5, update the minimum, but then it sees 5 is bigger than 1, updates again, and completely misses that -3 was the actual smallest.
Exactly. And the source points out that trying different lists, like 1, 4, 0, 3, 2, would also reveal the problem. You got to test it with different arrangements of numbers to make sure it works in all cases.
So hand tracing is like a way to really see the inner workings of your code step by step. Now, another technique that sounds a bit more straightforward is adding extra output statements. What's that all about?
This one's pretty simple. You temporarily add these print statements in your code, so it'll show you the values of certain variables while it's running. It's like leaving breadcrumbs for yourself so you can see what the program is thinking at different points.
So you can see if the numbers are what you expect them to be.
Exactly. If you think a calculation's going wrong, you can print the values before and after, and that'll often tell you what's up. And once you've found the problem and fixed it, you just remove those extra print statements.
They're like temporary scaffolding for your code.
Yeah, a good analogy. Now, our source material also mentions these more advanced debugging tools, things like visualizations and debuggers.
Those sound pretty high tech. What do they do?
Visualizations, they're like taking that idea of understanding your program's state and making it, well, visual. They use graphs, charts, even colors to show how data is moving and changing. Super helpful for complex programs where just looking at numbers might not be enough. And debuggers, they're like the ultimate bug squashing tools.
Oh, so they're like specialized software for this.
Yeah, they have all sorts of features. You can pause the program at any point, go through it line by line, see all the variables, set breakpoints to stop it at specific places. You can even change variable values on the fly to test different things.
So you have a ton of control over how the program runs.
Exactly. These tools, they're like giving you X-ray vision into your code so you can really see what's going on. Now, shifting gears a bit, we've talked a lot about finding and fixing errors, but when in the whole process of building software, should programmers be thinking about this? Is it like at the very end, after everything's written?
Yeah, I was wondering that too.
Well, a key takeaway from our source is that you should be thinking about testing, like from the very beginning, even before you write any code. You got to define what the program is supposed to do, how you'll know if it's working correctly. Those are the program specifications.
So before you even start coding, you're thinking about how to test it.
Yes. And those specifications, they guide you in creating your test cases. If you know exactly what the program should do under different circumstances, you can design tests to check those behaviors. Thinking about testing up front, it actually helps you understand the problem better and can prevent errors in the first place.
It's like having a blueprint, not just for building the house, but for making sure it's structurally sound. Now, our source revisits that minimum finding algorithm and gives a few example lists, asking which one would best expose the error. They highlight list C, which was 9, 7, 6, 4, 8. Why was that one so effective?
Because with that list, the faulty algorithm would pick 4 as the minimum, which is wrong. Remember how it only compared each number to the one after it? Well, in that list, when it gets to 4, the next number is 8, which is bigger. So it just stops there, thinking 4 is the minimum. But it completely missed the 6 and the 7 earlier in the list.
It got tricked by the increasing order at the end. And there's another example, a simple algorithm that checks the temperature, and if it's 32 degrees Fahrenheit or below, it displays a message like, "Watch out for snow." What kind of test input would reveal a problem there?
Here, you'd want to use a border case, that critical value right on the edge. If the code was accidentally written to check for temperatures strictly less than 32, well then an input of exactly 32 degrees wouldn't trigger the message. But 32 degrees, that's freezing, it could snow. Testing that boundary value, it shows you if the code is behaving as intended.
It's like that saying the devil's in the details, but in this case, it's the errors that lurk at the boundaries. So it seems like it's this constant cycle, right? You define what you want the program to do, you write code, you test it thoroughly with different inputs, including those border cases, you analyze the results, you revise the code, and you test it again.
Exactly. And it doesn't necessarily end when the programmer thinks it's perfect. Our source emphasizes that even after all the testing, when the software is released to users, they might use it in ways that programmers didn't expect, and new issues might pop up.
So real-world use can uncover even more errors.
Absolutely. And that leads to more revisions, updates, patches. It's an ongoing process of improvement. The takeaway here is that errors, they're not a sign that you failed, they're just part of the process, part of the journey of creating complex things. It's not about eliminating them completely, that's often impossible. It's about understanding them, anticipating them, and having strategies to deal with them when they show up.
It's like errors are inevitable, but how you handle them, that's what makes the difference. And one of the most powerful ideas from our source is that you should be thinking about how you're going to test your code even before you write it. It's shifting the focus from just getting the program to run to making sure it runs correctly, reliably, under all conditions.
Yeah, it's about building that mindset of quality and reliability from the very start.
So, as we wrap up this deep dive into the world of programming errors, I want you to think about this. How can these principles of finding and fixing errors apply to other areas of your life, beyond coding? Think about situations where you're trying to solve a problem, learn something new. What assumptions are you making? How can you test those assumptions? Where are the potential pitfalls?
It's about applying that same careful analysis, that same attention to detail to any challenge you're facing. It's about not being afraid of errors, but seeing them as opportunities to learn, to refine your thinking, to ultimately create more robust solutions, whether you're writing code, designing a product, or even just navigating the complexities of everyday life.
It's about bringing that programmer's mindset to everything you do. Thanks for joining us on The Deep Dive.
Until next time.